Hello, my name is Germán Vidal. I come from the Valencian Research Institute for Artificial Intelligence at the Universitat Politécnica de Valencia. And today I'm going to talk about the computation of message races and race variants in the context of a message passing concurrent programming language with selective receives. Well, let me start with some motivation or introduction. In the last years, we have defined a framework for reversible debugging in the context of a message passing concurrent language like, for instance, Erlang. We have also developed a debugging tool for this language, which is called Coder. This has been done in collaboration with Naoki Nishida from Nagoya University, Ivan Lanese from Bologna University, and my PhD students Adriana and Juanjo. So the main features of this framework are the following. So first we consider what is called causal consistent reversibility, okay, which means that we don't need to explore a computation backwards in exactly the opposite order of the corresponding forward computation, okay, but we let the user focus on undoing the actions of any arbitrary process as long as before undoing an action we first undo all the consequences of these actions. That means, for instance, before undoing the spawning of a process, we should first undo the actions of this process. Or before undoing the sending of a message, we should undo the receiving of this message. But this is somehow transparent to the user. So the user just focuses on a process and starts undoing the actions of this process or exploring the computation backwards. And the user can let the debugger take care of undoing all these consequences, right? And secondly, rather than considering traditional breakpoints, we introduce a notion that we call request, which typically have the form go backwards up to the point where this message was sent, or go backwards up to the point where this process was spawned, and things like that. Okay, so it's a convenient way of exploring a computation backwards. So our aim with this work was to improve this framework with some additional information. So first we wanted to introduce the computation of message races, because when we are exploring a computation and we have a number of receive actions, in principle we know which are the messages that have been actually received. But it might be the case that for some receive actions, for some receive statements, other messages could have been received too, okay, in a non-deterministic manner, and the user could be interested in exploring these alternative executions, okay? And actually, for this purpose, we introduced the second notion of race variant, which is essentially a sort of trace or partial trace that can be used by the debugger to explore these alternative executions, okay? So I will give you more details in the following. Okay, this is the setting that we consider in this work. It's a typical message passing concurrent programming language that mainly follows the actual model. Here each process is identified by a unique identifier that we call PIT. Each process has a local mailbox that is private, I mean it's not visible from outside the process. Communication is asynchronous and is based on message sending and receiving, so we don't consider shared memory in this work. And moreover, receive statements are selective or can be selective, which means that a process does not necessarily consume the messages that are, say, delivered to the mailbox of the process in exactly the same order, right? Because we have some additional, or we may have some additional constraints. This is the case, for instance, of a subset of the language Erlang. Let me illustrate the language that we consider with a very simple example. Okay, so you don't need to focus on the text. This is essentially pseudo Erlang. Okay, you can just look at the diagram in the right hand side. So here essentially we start the computation with a process that we call P1. Okay, P1 is the PIT of this process. And then this process performs three actions that you can see here. So first it spawns another process that we call P2, then it spawns another process that is called P3, and finally it sends a message, which is a tuple of this form with the constant val, okay, the number 1, And well, we have a label. This is not part of the language, but it's introduced in our framework by a program instrumentation because this is useful to uniquely identify the messages, okay? So then if you look at P3, okay, this process here, it sends another message with a similar form, a tuple with the constant val and the number 0. And finally another message, again a tuple with the constant val and in this case the number 2, which are labeled with L2 and L3 respectively. Okay, and if you look at the code of P2 here, this is a receive statement, but it doesn't consume the messages in the order they arrive, but we have some additional restrictions here in red. The first one says that it can only consume a message if it has this form, a tuple val with some number m, and m is greater than 0, okay? Or if the message is exactly the constant error, right? So that means in particular that this message cannot be consumed by this receive statement. Therefore, even if in principle one could say, okay, here we have a race between messages L1 and L2, that's not true, okay? Because this receive is selective, and actually we can only have a race between L1 and L3, right? Well, some years ago, we introduced at FORTE 2019 an extension of the original framework for record and replay debugging. So essentially the idea is to instrument the source program so that when it is executed in the standard environment, it produces as a side effect a log or a trace of the execution. So this log is essentially a mapping from bits, from processes, to a sequence of global actions, and in particular we only need 3 global actions: spawn P, which represents the spawning of a new process with P, and send and rec L, okay, these 2 actions that denote respectively the sending and receiving of a message with label L, okay? So for instance, for the previous execution, our log has this form, okay? So here we have that P1 spawns P2, spawns P3, and sends message labeled with L1. In principle, we don't have the value, the message value, or any other information. So for P3, we have the sending of 2 messages, L2 and L3. And for P2, we only have one action, which is the receive of message L1, okay? And observe that this is not, this is just a partial order, so we know what are the actions of each process, but we don't know, this is not fixed in the log, how these actions are interleaved in a particular execution, right? So the first question was, can we use these logs for computing message races? That would be great. And well, indeed, we have proved in the FORTE paper that I mentioned before that these logs contain enough information for causal consistent replay in our debugger. But unfortunately, it's very easy to see that they don't have enough information for computing message races. Well, some obvious limitation can be seen here, where if you look at the send events, okay, send L1, send L2, or send L3, we don't know what is the bit of the target message, okay? We don't know to which process these messages are addressed, and therefore, if a message is not received, it's impossible to know whether there is a possible race between L1 and L2 or L1 and L3, okay? Because we don't know that the target of these messages is the same process, P2. A second not so obvious limitation is that if you look at these 2 diagrams that are in principle different, if you look at the order in which the messages are delivered to P2, okay, so in the first diagram they are delivered in this order, L1, L2, and L3, and in the second diagram the order is different, it's L2, L1, and L3. So by looking at the first diagram, one can say that there is some potential race between L1 and L2, okay? And however, in the second diagram, this potential race could be between L1 and L3. L2 is, say, in the past of this receive. So if it was not received, despite the fact that L2 arrived before L1, is because obviously the message of this, the value of the message L2 doesn't match the constraints of L1, okay? Therefore, in the second diagram, we can only have a race between L1 and L3. Unfortunately, the log of these two diagrams is exactly the same. Okay, therefore there are several obvious limitations, and we need to add some more information in order to be able to compute message traces using these logs. Well, a first solution consists in making message delivery explicit. That is, we can have, rather than just two actions associated to message sending and receiving, we can have three actions: message sending, message delivery, and message receive, okay, or message consumption, because delivery and consumption might be different, so the order in which messages are delivered and the order in which messages are consumed might be different. So if you look at this second diagram, the order in which the messages are delivered is L2, L1, and L3, but L1 is consumed first. And this is typical when we have selective receives, okay, because there are some additional constraints, and it could be the case that the value of message L2 doesn't match the constraints of this receive, okay? So that was a first solution that we tried, but unfortunately that's not enough, okay? Because if you look, for instance, at the first diagram, even if we have the information about the order in which messages have been delivered, we don't know whether the race is between L1 and L2 or between L1 and L3, because it depends on whether the values of messages L2 and L3 match the constraints of this receive, right? So in practice, our proposal consists in extending the logs that in the following we call traces instead of logs in this way. So we keep the first action, spawn P, exactly as it was before, but now we extend the action send and receive with some additional information, which is in red here. So if receives were not selective, we only needed to add P here, okay? So the bit of the target of this message. But since receives are selective, we also need to add the current value of the message and the current constraints of the receive statement in order to be able to check whether the message value matches the constraints of the receive statement, okay? Let me now show some details of our approach. So first we consider, rather than considering a particular programming language in this work, we consider sort of abstract model of computation. And here the key notion is the notion of interleaving. So essentially an interleaving is a sequence of events of this form. So an event is a pair where the first component, Pi, is the bit of a process, the process that is performing an action, and the second component, A sub I, is an action that could be any of the three actions that I have shown before, okay? But that's not enough, as I mentioned before. I mean, if we consider a particular language and we generate these interleavings by instrumenting the source code that is then run in an actual language environment, then we know that by construction these interleavings are correct. But here we consider, as I said, an abstract model, and therefore we need some additional conditions on these sequences of events in order to be a valid, a legal interleaving. So these conditions are very intuitive and are these ones. So first, the bits and the labels of an interleaving must be unique, so we cannot spawn two processes with the same bit or send two messages with the same label, okay? A process cannot perform any action before it is spawned, which is quite intuitive, quite obvious. A message cannot be received before it is sent, again very obvious. The value of a received message should match the receives constraints, because we have selective receives. And finally, and this is perhaps a little bit more subtle, the messages between any given pair of processes must be received in the same order they were sent, unless they didn't match the constraints of the receive, okay? Which means that between two given processes, we cannot swap the order in which these messages are delivered, right? For instance, for the previous diagrams that I showed before, okay, we have these associated interleavings, okay? Yeah, the main difference is the order in which messages L1 and L2 are sent. In the first interleaving, we can see that first we send L1 and then L2, and in the second interleaving is the other way around, okay? As it is usual, given an interleaving, we can introduce an associated happen before relation, Lampot's happen before relation, which is defined in this way. So given two events of this form, okay, we say that the first one happens before the second one if one of these conditions hold. So the first condition essentially means that the actions of a given process cannot be swapped, are fixed, okay? And therefore, if the process is the same, if Pi and Pj are the same Pit, then we always have that an action of this process must happen before the subsequent actions of the same process, right? So we have a clear dependency between the actions of a given process. The second condition, intuitively, means that the spawning of a given process, Pj, must happen before any action performed by this process, right? And the last one says that the sending of a message must happen before the receiving of the same message, okay? Note that the label L and L is the same in these two actions. Well, actually, the happen before relation is the transitive closure of this relation. And then we also say that two events, Ei and Ej, are independent when none of them happen before the other, okay? So they have no dependency between them. And now we can introduce a key notion, which is the notion of causal equivalence, in which we say that two computations or two interleavings are causally equivalent. Intuitively speaking, they produce the same outcome if one of them can be obtained from the other by a finite number of swaps of consecutive independent events, okay? Because in principle, independent events, the relative order of independent events is not important, right? They have no dependency, so we don't care whether one happened first or the other. Therefore, if by swapping these independent events you can go from one interleaving to the other interleaving, it means that they are essentially producing the same outcome. They are equivalent, they are causally equivalent, okay? And this is a key notion in this framework. So consider, for instance, our usual example with these two diagrams and the corresponding interleavings A and B. Well, these two interleavings are causally equivalent, okay, because we are only swapping independent events. In the first interleaving, we first send message L1 and then L2, and in the second interleaving is the other way around. Okay, you can look at these two diagrams and say, okay, it's not so obvious why these two interleavings should be causally equivalent, because it seems that the message race could be different in these two interleavings. There's a subtle point here, and it's the fact that we are assuming that both A and B are actually interleavings. And that means that this sequence of conditions here must hold for these interleavings. And this is a key point here, okay? Because if you look at the second interleaving, okay, B, where we first send message L2 and then L1, okay, this is still correct because, as we have seen before, the value of this message, V2, doesn't match the constraints. So therefore, we can swap the sending of L1 and L2, and that's still fine. That is, and this is still an interleaving. If the message V2 would match the constraints of this receiver statement, then V would not be a correct interleaving, right? Because to be a correct interleaving, it should have received message L2 rather than message L1. Okay, so this is a little bit subtle, but it's quite relevant. Well, and finally, this is clearly not causally equivalent interleaving. It's not causally equivalent to the previous ones, because in this case we have swapped these two actions of process P3, right? So now, in order to compute message races, we are not going to use interleavings, but we use traces, which similarly to logs are mappings from pits to sequences of actions. That is, they don't represent a total order, which is the case of an interleaving, but just a partial order, similarly to the logs that I mentioned at the beginning of this talk. So Actually, in the paper, we have proved that a trace represents all and only the interleavings that are causally equivalent. So we have a one-to-one correspondence between a trace and a class of causally equivalent interleavings. And that's a very nice result because, well, on the one hand, these traces contain enough information for computing message races and producing race variants that can drive the replay of an execution. But in contrast to other approaches like stateless model checking, we don't need to apply a dynamic partial order reduction technique, okay? Because if we work at the level of traces, they already represent, I mean, if two traces are different, we know by construction that they represent different causally equivalent classes of interleavings, right? And this is a very nice result in my opinion. For instance, if we consider the usual example with these two diagrams and the corresponding interleavings, both diagrams and both interleavings can be represented by a single trace of this form, which is, well, very similar to the log that I showed you at the beginning. The only difference is that now we have some additional information in some of the actions, but otherwise it's the same as before. So this is just a partial order in which we know what are the actions performed by each process, but we don't know how these actions are interleaved in an actual execution, okay? So for each possible interleaving of these actions that is, say, legal, that is valid, we have a corresponding interleaving. For instance, possible interleavings associated to this log are A and B, okay? Let me now introduce a declarative notion for message race, okay? So we consider a particular trace tau in which, well, we have a receive action in which message label L is received. So we say that there is a race between L and L prime, okay, between these two messages for this receive, for this particular receive, if there exists a subtrace. And, well, essentially this notion of subtrace means that the sequences of actions of each process are a prefix of the corresponding sequences of actions in the original trace. So this is what we call a subtrace. So if we can come up with a subtrace of the original trace in which the actions of process P, okay, are the same up to the point of this receive in which we have changed L by L prime and we have removed the subsequent actions, okay? And in order to be a correct trace, okay, because this should be a trace, there are some implicit conditions that are not shown here, but that must hold. So, for instance, we cannot remove the spawning of a process if we keep the actions of this process. And we cannot remove the sending of a message if we keep the receive of this message, etc. So this subtrace, there are some conditions for this subtrace, okay, that are implicit by the fact that tau prime should also be a trace. So we are not concerned on how this subtrace is constructed here. So this is just a declarative notion. If we can find such a subtrace, then there is a message race between L and L prime. Now we show constructive definitions for message race and race variant. Okay, well, you can find the details in the paper, but let me just show the basic ideas because I think it's not that difficult. So we say that two messages L and L prime race for a given receive statement in which the first one, L, has been received if the following conditions hold. So the first one is obvious. So we have send actions for L and L prime in which the target process is P, is the same, okay, the process that is receiving this message. Secondly, both message values V and V prime should match the constraints of the receive statement. And this is a little bit more subtle. Using the happen before relation, we should check that the received didn't happen before the sent of the alternative message L prime, because otherwise note that in a possible race variant, in a possible alternative execution, we want to change L by L prime, right? But if we have a dependency, removing the receive of L would also remove this sent action, and therefore this alternative would not be possible, right? And finally, if there are several messages that say for which all these three conditions hold, okay, we should check that this L prime is the first one that matches the constraints of the receive. Okay, so this is essentially required in order to guarantee that the messages are consumed in the order they are delivered, assuming that they match the receive constraints, right? Or in other words, a receiver statement should consume the oldest message that matches the constraints of the receive. And then we have the notion of race variant, which is very intuitive and can be constructed as follows. So the idea is that, so if we have a race between L and L prime, so the first thing that we do is take the trace and remove this receive event, the original receive event of message L, by a variant of this receive event in which we receive L prime instead. Okay, everything else is the same. Second step, we delete all the subsequent actions of this process that received message L and now L prime. Okay, because remember that we have a dependency between an action and the subsequent actions of the same process. Therefore, everything that happened after the receive of L prime, well, perhaps is not there anymore, and we have to remove these actions. And finally, we have also checked transitively all the actions that depend on the actions that we have deleted and delete them as well, right? So it's like a recursive definition where we keep deleting actions and the dependencies on these actions and the dependencies of that actions, etc., until no more actions are removed. Okay? So as I mentioned, well, this is more or less the intuitive idea, but you can find all the details in the paper. Well, to conclude, in this work we have introduced a new method for computing message races and race variants in the context of a message passing concurrent language with selective receives, like for instance a subset of the language Erlang. A result that I find quite interesting, as I mentioned before, is that in contrast to other standard techniques like stateless model checking, dynamic partial order reduction is not needed in our case because the traces already represent classes of causally equivalent interleavings. Okay? Indeed, our traces are more similar to the scene sequences of another technique that is called reachability testing. Well, the focus is different. There are several differences. For instance, they don't consider selective receives or dynamic process spawning. They consider pods instead. And as far as I know, they don't prove that a scene sequence actually represents the class of all causally equivalent executions. But anyway, the key point is that both our traces and the scene sequences are, say, mappings from processes to sequences of actions. Therefore, they represent a partial order. Okay, that's an obvious similarity with this between traces and scene sequences. So as applications, we have already extended our debugger coder with the computation of message races and race variants. Okay, so in this case, when the user is replaying an execution in the debugger, he or she can check whether in a receive statement we have some alternative messages that are racing for this receive, and then we can produce race variants so that the user can use these race variants to explore alternative executions. Okay, and in the medium or long term, we would like to add more general requests. So the current request just consider a single computation, like go forward until this message is sent, or go forward until this process is spawned, etc. But thanks to the computation of message races and race variants, we could come up with requests that consider the complete execution space. Things like go forward until something bad happens, go forward until an orphan message is produced, go forward until a deadlock happens, etc. And when something bad happens, we can then change to the debugging mode, okay, and explore this particular execution in order to find what is the source of the error, right? And that's it. Thanks for your attention, and if you have any question or comment, please don't hesitate to contact me.